All right, this is the first video in our chapter on gases. It's kind of a short chapter, and we're just going to take a look at some of the properties of gases and then investigate a little more closely things like gases and their relationship to pressure, temperature, volume, look at some of the gas laws. So to start off with, I had you guys do a reading assignment, and you had to fill in on this page the details of something called the kinetic molecular theory. And this pertains to gases, and it's kind of the rules for gas behavior. It's what they, how they behave, what they do. So, excuse me, we're going to talk about each of these points and explain how this relates to how a gas behaves. So the first component to kinetic molecular theory is that gases consist of large numbers of tiny particles that are far apart relative to their size. So what we're talking about here is density. This means that gases, and I'm just going to do little letters here, are not dense. They are not dense at all. And so because of that, they can be compressed easily. So they're easily compressible. Because those gas particles are far apart, it's easy to squeeze them together. This also means that they can they always take the shape of the container. Well, in a sense, we don't even think about taking the shape. They always fill the container. And this gives us the trait. So often when we're talking about the fact they're far apart, we talk about, I'm going to put the traits in red. So we're dealing with volume here. Point number 2, collisions between gas particles and between particles and containers and container walls are elastic collisions. There is no loss of kinetic energy. And I want to jump down to point number 4. There are no forces of attraction or repulsion between gas particles. So what we're talking about here in points 2 and points 4, I'm going to kind of bring a sidebar out here, are the rules. So these are a couple of the rules. You know what? I'm going to cross that out. I'm going to say ideal behavior. Ideal behavior is a better way to say it. And when we talk about ideal behavior, think about if you were a teacher and you wanted to talk about the ideal student, it would be a student who showed up every day, always did their homework, participated in class, and gave their best effort. So none of us really fit that. And, even as teachers, we have the ideal teacher. We don't always operate in ideal ways. Maybe we're tired, or maybe we're hungry, or maybe we've had a really bad day and we deviate from this ideal behavior. But what these 2 points give us is what we'd like to consider gases do. So under ideal conditions, you're going to get point number 2 and point number 4. Now you really need to remember, I'm going to do these guys in green. You don't really need to remember points 2 and 4. I'm not going to ask you guys to regurgitate this on a test. But what I want you to understand is that all of these laws that we're talking about assume that our gases adhere to these ideal conditions. And so when we are dealing with the assumption that we're working with these 2 points, and basically what these points are saying is that if a particle bounces off a wall, it comes off with the same velocity as it entered with. And that the gas particles aren't causing, they're not sticking together or pushing each other apart. So that any motion that happens is dependent, what we're going to see is it's dependent on temperature. So again, this is the ideal. And so we'll talk about gases that would adhere to ideal behavior are called ideal gases. So these are our parameters for ideal gases. And what I do need you to know is that there's a difference between ideal gases, and if you're not an ideal gas, then we call you a real gas. And if you think about it, there really isn't any such thing as an ideal gas, because we're always going to have variables that we maybe don't consider. So, but for all of the equations we're working with, we assume we have an ideal gas. And that's listed in the kinetic molecular theory. Point number 3 here. Gas particles are in constant rapid motion. So this one is kind of tuned into number 5. Gas particles are always moving. And the movement, so kinetic energy, let's talk a little bit about what kinetic energy is. We talk about energy, screen here, and we talk about the fact that we have 2 kinds of energy. We have potential energy, which is stored energy. And these are kind of the, 9th grade definitions that you guys had. Potential energy is stored energy. And kinetic energy is energy of movement. Energy of movement. So when we talk about the average kinetic energy, we're talking about energy of movement here, movement energy. So these guys are moving constantly, and it's random and it's rapid, and we don't have anything that's impeding it. So that's points 2 and 4. And what we say is that temperature is directly dependent on this movement. In fact, temperature is a measure of the movement of particles in a substance. You may remember from other classes that when we talk about atoms or molecules that make up atoms in an element or molecules in a compound, that they're always moving. There is always motion. Even in solids, we get vibrational motion. So even the desk that you're sitting at right now or table you're sitting at right now as you watch this, those molecules are moving, even if they're only vibrating. Now with gases, we get all kinds of movement. We get rotational, we get vibrational, we get linear, they're moving back and forth through the walls. So what we see is that while all solids, liquids, and gases all have particles that move, with gases it's special because they're so free, because they're not dense, because they're so far apart, we get this, excuse me, really a high energy in gases. And we measure that energy by temperature. So temperature, at the higher the temperature, the more those molecules are moving. So this is, I'm going to circle in red, one of the other traits we're going to talk about, temperature. So temperature applies to points 3 and 4. And then one of the ones that I forgot was up here for part 1. When we talk about particles that are far apart and they fill their containers, so that's volume. The fact that they're easily compressible, this is going to take us to the factor of pressure. So when we change the size of the container, we're compressing the gas, we're increasing the pressure. When we decrease the size of the container, we're increasing the volume, we're dropping the pressure. So what we're going to see is that there are relationships between volume, pressure, temperature, and let's see, we're going to write this. Let's write this up. So we have relationships between pressure is P, volume is V, temperature is T, and the amount of matter. The amount of matter, which we've learned in another chapter, is the mole. So we're going to start off and we're going to look at 2 of these, like we'll do pressure and volume, then we'll do pressure and temperature, then volume and temperature, then all 3, and then we'll bring all of these together. So we're going to kind of slow walk our way up to all of these relationships. Okay, I think that is probably good enough for this video. So we will call that I don't know. You know what? I'm going to add units. I was deciding whether or not I wanted to add units. So I'm going to go ahead and pause the video, get the next sheet. Okay, so at the top of the next page, you'll see that we have units for gases, units. So we're going to be talking about units for volume, units for temperature, and units for pressure. Volume, the unit is the liter. And if you remember, we have when we came up, we talked about liter, and we said that this is not a base unit. We had base units, we had derived units. We said 1 milliliter is actually equal to 1 cubic centimeter. So we take the base unit of distance and we cube it, and that gives us a mil. So sometimes you'll see volume listed as cubic centimeters, but you need to remember that a mil and a cubic centimeter are the same thing. For temperature, we have 3 scales. The one that we use in America is Fahrenheit. We're just going to toss that one out. So the other 2 that we have are Celsius and Kelvin. And Kelvin is the SI unit, believe it or not. Although in a lab situation, we're always going to use Celsius. So if you take the Celsius value and you add to that 273 degrees, that gives you the Kelvin value. So if you want to convert Celsius to Kelvin, you have to add 273. And if you're going to go Kelvin to Celsius, you have to subtract 273. So it's a pretty easy conversion, and you do need to know that. All right, finally, we have pressure. There are 2 forms of pressure that we talk about. One is atmospheres, and that's abbreviated ATM. And if you think about it, how many atmospheres are you sitting under right now? 1. So there is 1 atmosphere of gas above you. At sea level, you're under 1 atmosphere. It's the pressure that's exerted by the atmosphere of the Earth. But this is not the SI unit. The SI unit is called the Pascal. And a Pascal is pretty small, so more often we usually talk about kilopascals. Kilopascals or kPa. And one of the conversion factors that you need to know is that 1 atmosphere is equal to 101 kilopascal. So this is going to be the most common conversion that you're going to have. Now, there are 2 other pressure units that you don't need to know. I'm going to jot them down. One is millimeters of mercury, and this comes back. This is an old one. They would put mercury in a column, and they would see how far it would move. And another one is torr. I'm going to skip those. I don't think for a high school level, you're really going to run into those much. And they're definitely not the ones you see the most. 9 times out of 10 in my career as a chemist, if I was dealing with pressure, it was atmospheres or kilopascals. So what are our takeaways? We have got, starting from the back going forward, we talked about the units for gases. Volume is a liter, temperature is, oh, I know one of the things I forgot. So when you're doing calculations, and we're going to mention this again, your values have to be in Kelvin. So you're going to have to convert everything to Kelvin for the calculations that we have coming. Pressure, we're most likely going to use atmospheres per kilopascal. You need this conversion unit. And then we also talked about the kinetic molecular theory of gases, where we had that they're large and far apart. This gives us the values of volume and pressure. We talked about ideal gases versus real gases. And then we talked about how movement is actually, temperature is a measure of movement. And that's the 3rd trait that we're going to, the 3 of the 4th traits that we're going to talk about with gases. All right, that's it for our introduction. Thanks for watching. That's all for now.